Start recording here. Okay. Slow up. So like I said, I didn't finish marking. I tried, but last night I had to admit defeat, and I wasn't gonna pull it off. So, but I will, of course, post your marks on Moodle as soon as you're done, and then hand them back on Monday. So you will get them back. Really kind of fun. So I did go through and see which ones you picked, and really kind of fun to see which questions you guys went for. Some surprises in there. And we're actually going to look at the numbers in these notes. So I think that's kind of fun. So you guys will be in the notes forever. No, until I change them at least. Let's see if I can. I know we want all the lights out, so it's nice and cozy, but I'll just do those overhead ones. Okay. So chapter 6 is, well, for one, it's our last inference section, right? So it's the last section, or 6.1 and 6.2 are the last types of hypothesis testing and confidence interval questions that we'll be doing. So, hooray. Maybe, I don't know. It seems like some people are okay with hypothesis testing. Tests look good so far, so I'm pleased. But so chapter 6 is dealing with categorical data, right? So far we've only talked about, okay, so we've got one sample means, we've got paired data, we've got two independent sample means that we're comparing, right? So far we've only talked about means, okay? Now we're gonna talk about how do we analyze categorical data. So remember categorical data, right? We have some counts in each category, right? And so what we do is we analyze the proportion instead. Okay? And so how I'm going to differentiate between a means question and a categorical data question is just means or proportions. Okay? So proportions question. Right, because we've got some proportion of people who chose to do matched pairs, for example. Right? Some proportion of people who have blonde hair, right? So we've got proportions for all these categorical variables. Here's where I stray a little bit because we said, okay, we use Greek letters for the population, but what I'm going to use for the population proportion, right? Because there's going to be some population proportion that we're trying to infer something about, right? I'm going to just use lowercase p because the Greek letter we would use is pi, but because pi is used, you know, in calculations, it's this number, and I'm kind of hesitant to use it. But if you want to use pi, that's great. But I'm just going to use lowercase p. And then for the sample proportion, we're going to use p hat. Okay? So the hat is basically the same as the x bar, right? Anything with a bar over top is an average. So that's why we can't use p bar. That's the average of p, right? So we have to use something else. Okay? So here, I'll just make a note. Can't use p bar since that would be the average of p. Okay. Use p hat for sample proportions. As you've probably noticed, right, it's important to keep track of, okay, what's from the population and what's from the sample, right? So that's why we have to have two notations, right? One for the population proportion and one for the sample proportion. If we do a little sneak preview on your formula sheet, so this one is on your old formula sheet, but it's also on the one I just handed out, the extra one. I'll just sneak it in here. Maybe. Formula sheet looks like this, right? I think I changed the order since one we have, but all the information is all the same, right? So if p hat is a sample proportion, right, already we can build a confidence interval, right, without even knowing really what's going on. You know, we know kind of what a proportion is, right? But we can already build a confidence interval just knowing p hat, because we need p hat. That's our best guess at what the population proportion might be. And then we know how to find a z star, right? That's the same as finding it for a means question. P hat, back in action, right? Q hat, remember from binomials, we said Q is just 1 minus P. And I've got that down here, so any Q is just 1 minus the P. So Q hat is 1 minus P hat, for example. Q star is 1 minus P star. Q naught is 1 minus P naught. And so we've got all these guys, and so we've got P hat, and then Q hat is just 1 minus P hat. Oh, I'm so zoomed in here. Better change my. Q hat is 1 minus P hat. Oops, nasty hat. There. And, well, that's just your sample size, right? So what's nice about proportions questions is that really you only need to know the sample proportion and your sample size, and already you can build a confidence interval, right? So there's not all this information that you have to keep track of like there was in the means questions. Same idea, right? If you've got, okay, so we took some sample proportion and we're going to want to compare it to some hypothesized proportion. That's the same idea as one sample means, right? We collected a sample of information, we found their mean, and we want to compare it to some value, right? And so same idea. We've got a sample proportion that we want to compare to some value P naught. And so now we're hypothesizing about P instead of mu. Right? We're always hypothesizing about what the population might look like. And so now we're hypothesizing about P. How does it relate to P sub 0, P naught? And wouldn't you know it? We'll talk more about why we can use a z-score. But for step 2 in our hypothesis testing, when we do the test, we're actually just going to calculate a z-score, which we already know how z-scores behave, right? We can use the z-table to find probabilities. But so to calculate the z, we need our sample proportion. We need our hypothesized proportion. That's fine. That's the same setup as for means, right? How far is your sample from your population? And then down here in the square root, you've got P sub 0 times Q sub 0. That's just 1 minus P naught. P naught, P sub 0. They're the same. Okay, so we've got P naught and then Q naught, which is just 1 minus P naught over N. So again, you only need your sample proportion, your sample size, and now you need your hypothesized proportion. And we're also going to look at same thing as the one sample means, where we were able to calculate, okay, well, what how big of a sample do we need to satisfy these criteria, right? We need to know what's our desired margin of error and what's the confidence level that we need to be at. So we'll do that one later. Okay. But just so you have an idea of what's going on, right? Because now you've done all this work doing hypothesis testing and confidence intervals, and so you're more comfortable with, okay, the idea, okay, so just give me a confidence interval, the formula, and I can figure it out, right? You can build a confidence interval, and it doesn't really matter what it's about, right? Because what you're gonna find is that you can do confidence intervals for anything that you can measure, right? So if you're drawing a line of best fit, for example, right, you're gonna have a slope and an intercept. You got it. You can build a confidence interval for the slope. You can build a confidence interval for the intercept, right? So anything that you can measure and estimate, you can build a confidence interval for. We're just looking at a few set ones. Same thing, you can do hypothesis testing for anything that you can do a calculation of. But like I said, we're just doing some set ones. But I like proportions. Or I like proportion questions because, well, there's not as much information that you have to deal with in the question, right? Try to figure out what's what, right? And also in the formulas, you don't have to, you really only need to know p hat, your sample size, and your hypothesized proportion if you're doing a hypothesis test. So p hat is your sample proportion. Okay? We're going to be talking about a success. Okay, so a success is going to be the same idea as for the binomial, right? Whatever number of people satisfy the criteria that you're looking for, right? If you're thinking back to the test, for example, that we'll talk about, how many people out of the 78 that wrote it picked a 2-sample means problem, right? That would be a proportion, right? How many people picked a 2-sample means problem? That's a success if someone picked it. And then out of the total number that wrote it, which is your sample size n. So p hat is just the number of successes in the sample over the total number of individuals in the sample, which is just your sample size. Right? And so that means we need even less information, right? Because to get your p hat, you need your n. Right? The only reason I've got them kind of separate is because sometimes I'll phrase the question as 23% of the 200 people surveyed, blah, 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 right? So then you've got the sample proportion already, and then I give you the sample size. Right? Or it could be something like, out of the 200 people surveyed, 150 said yes. Right? Then you've got a proportion that you can build, right? Because then you've got 150 successes out of 200, and that's your sample proportion. So I guess I already spoiled it because the proportion follows a normal distribution, which is kind of weird to think about categorical data following a normal distribution. And so for that reason, we're going to put more emphasis on checking the assumptions. I haven't really been checking assumptions because there's nothing we can do, right? We're going to do a t-test no matter what. And then we're just going to say, okay, well, our inferences can be limited by these factors, right? So we just kind of highlight why we maybe shouldn't have done it, but we have to do it anyways. Whereas in this case, for proportions, we're going to have to check these assumptions. So as well as doing your hypothesis test and your confidence intervals, there's this added step of having to check your assumptions. So we'll talk about what those assumptions are. One thing I noticed that actually so the bottom blurb on the first page, just as the sample average would change when we take new samples, right? So does the population proportion, or so does the sample proportion, sorry. And we can develop a sampling distribution of p hat. We're not gonna, I'm not gonna test you on it like I did for the sampling distribution of x bar, but same idea. And so this little side note, I know it's hard for you because they're on printed pages, but this little margin note here is not important, but wouldn't really be doing my job if I didn't talk about some of the theory behind it, right? So we've got the sampling proportion, or the sample proportion p hat follows a normal distribution as long as you have large sample sizes. And so in our assumptions, we'll build that in just to make sure that our sample sizes are large enough. Okay? But if they are, then p hat follows a normal distribution, which is why we can use the z-score with a mean of p, so it's centered on the population proportion, and a standard error of p times, well, q, right, 1 minus p over n square rooted. So that's where the square root of p times 1 minus p over n comes from. It's the standard error. Any questions so far? Oh, I guess I should say, so after today, you'll be able to do, so I gave you assignment 6 because, I mean, with the notes, you will be able to do all of assignment 6 after today, but we're not going to have talked about together probably question 2, because that's going to be 2 sample proportions that we're comparing. Okay. But with the formula sheet, with the notes, I guarantee you can figure it out, but just as a heads up, we're not going to be doing question 2 until Monday. Okay. So, and possibly the last part of question 1, we'll see where we get to. Okay, so for these assumptions, right, for us to be able to say that something follows a normal distribution, we have to check, well, a lot of things. First thing we have to check is that we have independent observation. So we have to have a random sample, or at least assume that we have a random sample. And so this section shouldn't really be called just checking assumptions. It's more about stating the assumptions, right? Because if we don't know if we have a random sample, well, then we're assuming that we have a random sample, right? And so, so it's more about saying, okay, here are all the things that I'm gonna have to assume in order to do this. Sometimes it'll say you collect a random sample, and that's great. Then you can just say it was a random sample. There's a 10% condition, which we've talked about before, back in the binomial section. Oh, we didn't have time to, we have to go back to the binomial. Sorry, guys. Forgot we haven't covered the binomial. No one stopped me. You guys are like, oh, okay, read up on the binomial. We'll go back, sorry, I forgot about my flight mishap day. So we are gonna cover the binomial, but after. So I guess then you'll know, okay, I'll spend more time on this then. Because we haven't talked about it. So we have to have a random sample, yeah. Not on that one. That one's just for the 6.2 formulas, I know. It's when I got away with having a 1-page formula sheet. Those days are over. I know, you wish. So the 10% condition is just saying, okay, if we want to have independent observations, then as a rule, we shouldn't be collecting more than 10% of the population. Because if we've collected, so it gets tricky because we want to have large samples, right? Large samples are good and we want to have large samples, but also if we've collected too much of the population, so more than 10%, then there's a risk that we've got, you know, siblings in there and we've got BFFs in there, right? And so those are not independent observations necessarily, right? And so, so the 10% condition is, I'm pretty flexible on it just because if you have a large sample, then that's great, right? That's really good. But the 10% condition is just something that you might want to mention if you have a really large sample and there's a chance that you have more than 10% of the population. Then you could say there's a chance that the independence assumption is being violated because I have more than 10% of my population. So those are just making sure that we have independent observations. The second phase is to check that we can actually assume that we have a normal distribution, right? So basically checking, can we use a Z-score? The conditions that we check here depend on whether we're going to do a confidence interval or a hypothesis test. So what you're going to do on assignment 6, for example, is you're going to read through all the parts and figure out, okay, am I doing a hypothesis test? Am I doing a confidence interval? Spoiler alert, you're doing both on both questions. But just as a rule, for the final, it'll either be a confidence interval or a hypothesis test. So then you're going to read through and say, okay, what am I going to be doing? And then only check those assumptions. If you know you're going to have to do both, then you may as well check both assumptions at the same time. Because the thing is, regardless, you're going to have to check these two guys, the random sample and the 10%. Yeah. Yeah. It is. So be ready. No, I'll prepare you. So if we're going to do a hypothesis test, then we have to have at least 10 expected successes and 10 expected failures. And so what that's kind of stemming to is we can't use a really small sample to detect really small proportions. And so how you check it is, remember the null hypothesis, which we haven't actually talked about, I've just shown you on the formula sheet, right? But our null hypothesis is that the population proportion equals some number, right? Our hypothesized proportion. And so how we're going to check it is you take your sample size times the hypothesized proportion and make sure that it's more than 10. Right? You just have to have at least 10 expected successes. Otherwise, you need to increase your sample size. Just as a note, all these assumptions, they're all going to check out. So it's not about that, right? It's not about, okay, one of these failed, so I can't do the question. No, they're always going to check out. It's just your job to show me that you have checked them. And so if you find yourself saying, no, the assumptions are not satisfied, then technically you can't go on and do the question, right? Because you're saying, oh, I can't do it. And then 10 expected failures, right? It's just n times q naught has to be greater than 10 as well. Notice that these aren't percentages, those are just raw counts, okay? Just because we're talking about categorical data, so counts in each category. If you're doing confidence interval, then you have to have at least 10 observed successes and at least 10 observed failures. So the smallest possible sample size that you could have is 20, right? You have to have at least 10 successes and 10 failures. Most likely, you're not going to get that perfect even distribution just from a sample size of 20, right? So you're going to have to bump it up. And so you're going to have to keep sampling until you have at least 10 successes and at least 10 failures. Otherwise, you can't use those values to infer something about the population. Down here, I've got the note about, it's important to remember that Q is 1 minus P, and, or the probability of a failure, right? Q is just for the failures, in air quotes. And then Q hat is 1 minus P hat. Q naught is 1 minus P naught. Q star is 1 minus P star. Right, so we're going to be dealing with all these P's and Q's. And what I've got is that this is just summarized as Q is 1 minus P on your formula sheet. Okay. Do I have anything else there? No. Any questions? So we'll talk about the hypothesis test, but probably from looking at the formula sheet and, well, now we've got this added step of checking the assumptions, you're probably on a pretty good path to doing a hypothesis test for proportions already. So like I said, we're going to have some sample proportion. So if we've only got one sample of proportions, right, or one sample proportion that we're talking about, then we have to compare it to some hypothesized value. Whereas later on in the next section, we'll have two sample proportions and we just want to compare, are they different or are they equal or is one more than the other, right? But for now, we have to figure out what this P naught is going to be. But same setup, null hypothesis always has the equal sign in it, and the default is going to be the two-sided test. Right? But we could test is P less than 30%. Okay. So then you would check P less than 0.3. Remember, percentages, proportions, probabilities are all the same. Right? So a proportion is just a percentage divided by 100. Or a percentage is a proportion multiplied by 100. Step 2, we already talked about, right? We're going to do the test where we use the hypothesized proportion, P naught, compare it to how far is our hypothesized proportion from our sample proportion. That's the exact same idea as x bar minus mu over S over root n, for example. Right? Just taking into account the spread, which for hypothesis testing is going to be the square root of P naught, which is the same value as here, and then Q naught, which is 1 minus P naught over n. So step 3, where we have to find the p-value. Well, now we've calculated a z-score and we know exactly what to do with a z-score, right? That's kind of way back where we started, right? And so now you have a z-score, you can find the area in the tail that you're looking for, right? Either your one-sided or your two-sided p-value, remembering that if you need a two-sided p-value for when you've calculated a z, you find the area in one of the tails and then multiply it by 2 to replicate it in the other tail. So an extra little step, but not too bad. Once you have your p-value, you just draw the conclusion the same way as we always have, right? And so this is just the exact same blurb that I've been copying and pasting all along. I figure each new section I should just paste it in there just so you have it in your notes. But if the p-value is less than the alpha level, so meaning if your value, if your z-score now is far enough out into the tail, then you can reject the null hypothesis, right? Because if you're far out into the tail, the area in the tail is really small, right? And so if your p-value is less than your alpha level, then you have enough evidence to reject H naught in favor of HA. If it's not, then you don't have enough evidence to reject H naught. Same idea as before. Any questions? So let's do my example. That's what I mean. This is you guys. Well, and my other section. They had the same idea, but a coffee shop one. No meerkats for them. It's because I couldn't think of a clever like business for a meerkat. Mortgage broker. I've used that anyways. So I've got two sections. And so I did the same thing for both of you, right? Where you have 4 questions to choose from. They're all the means questions, and you choose 2, right? The choosing 2 is making it a little bit tricky to wrap your head around, or might make it a little tricky to kind of figure out what to do with these numbers, right? Because if there's 78 students that wrote it, I've got that down here, but I should have sent it up there. I'll just say here that N is 78 times 2 questions. So number of questions, right? If we're just bringing it down to, okay, no matter who wrote what, right, what questions were selected, then we've got 2 times 78 questions selected, so 156. So number of questions, so 78 students, 156 questions. Could have boiled it down to just which one did you pick first? Or I should have done a survey at the front. What's your favorite question type? Because now I'm just assuming that if you decided to do it, that's your favorite, which might not necessarily be the case. I don't know. So, or maybe you don't have a favorite type. In that case, I'm wrong. So anyways, out of the 156 questions that were written, then 25 of those questions were the sigma known, right? One sample means sigma known. 48 of those were the matched pairs. 40 of those were 2 sample means, which kind of I find really surprising. I'm impressed actually that people chose the 2 sample means, and it might be because it's, you know, easy to identify. Right? You've just got 2 groups that you want to compare, and so you feel like it's a sure bet. And like I said, that's probably what I would do, but I don't know. I'm just proud of you guys for picking the paired and the 2 sample means as your faves. And then sigma unknown got a solid 43. But I feel like, yeah, the sigma known was not the favorite, it seems. Looks like only 25 of those were written. So I looked at, okay, well, what are the proportions? Right? The proportions are just the counts over 156. But here they are, and so 30% of the 30.8% of the questions written were the matched pairs. And so what I did is I kind of worked backwards and I said, okay, well, looking at these numbers, it looks like the matched pairs is the favorite. And so I'm going to see if, so I'm going to do a hypothesis test to see if it is actually the favorite. Okay? And so just as a side note for lab 7, right, this is what you'll be doing. And so you'll have some proportions, right? And then you'll want to kind of formulate a hypothesis that you want to test around that. Right, and so that's kind of what I did here is I looked at this and said, oh, okay, this one's the highest, right? Is it significantly higher than all the others? How we test that is going to be, okay, well, if they were all the same, right, which is always the case for your null hypothesis, is that, okay, well, all these groups, they're all the same. One isn't higher than the other, one isn't lower than the other, right? If we've got 4 groups, then what we would expect to see is 0.25, 0.25, 0.25, 0.25, right? Just split it all across 4. So is there evidence that paired data is the preferred question type, and are the assumptions for inference satisfied? So here, I've just kind of discussed, okay, so how do we get to that 0.25? And that's a trick that we use quite often, right, is where we say, okay, well, if two groups are the same, then the hypothesized proportion that we're comparing them to is 0.5, right, 0.5, 0.5. If they're different, one of them is going to be significantly different from 0.5, right? So I've just established that, okay, for them to all be the same across 4 groups, I have to split my probability into quarters, right, 0.25. And so here, right, my P naught has to be 0.25. So P naught, oops, is 0.25. First thing we're going to do is check these assumptions. And so what I've done is I've just given you an idea of how to approach these, right? First stuff we had to talk about was, well, were these guys randomly selected? To be quite honest, no. It's everyone in my sections, right? And so, but there's other sections of stats. And so what I've argued here is that it's reasonable to assume that the 78 students in my classes are randomly selected from everyone who's taking stats this term, right? Just nice, healthy mix, right? And so that's an assumption that I'm making, right? And so may or may not be satisfied, but at least I've said, hey, here's what I'm assuming. I'm assuming that these 78 students who wrote the test are all independent of each other. Judging by the strong wet presence in this class, maybe that assumption is not really valid. Right? You guys are all in a group. But anyways, it's an assumption that I'm making, and then I can just go on. Right? And so the 10% condition, again, I'm just going to say we will assume that 78 is less than 10% of the population of statistics students. I don't know what that is. Is it at the college? Is it in Canada? I haven't specified, and I'm trying not to specify. I'm just saying, hey, here's something I'm assuming. All right, so a lot of the time this is how it goes, is you say, okay, well, I know there are these things that I have to check, right? And I'm just going to have to kind of assume my way to it. So because we're doing a hypothesis test, there's no mention of a confidence interval quite yet. We haven't talked about them really. So we're just going to check the assumptions for a hypothesis test. And so what we have to do is we have to check, okay, are there at least 10 expected successes and 10 failures? Meaning, in a sample of 78, if we have 4 groups, right, are we expecting to see at least 10 successes in each group? 78 split into quarters is 19.5. That is more than 10, right? And so we get a little check mark here just for fun. Same thing, the expected number of failures is going to be 58.5. And so we get a little check mark here. So you just do this calculation, make sure it's bigger than 10. If it checks out, then you move on, which it will. So we've narrowed it down to, okay, we're talking about a success is whoever selected a paired question. Right? And so we've got our sample proportion. It's pretty fun because I usually, and most people just use p hat in their R code, but it's like pH hat. I don't know. guys are too young for that. But anyways, it was a thing, and I can't remember when. Anyone remember? When were we? Yeah, when were we into the pH fat? Anyways, probably good that I can't remember what it stands for. But anyways, so we look at the sample proportion, 0.308. Let's just round it to 3 decimals for this question. I'll tell you what to round it to, or I'll try to give you a nice value that you don't have to round on the test. We'll see what I can pull off. And so what I've got here is, I'm just going to round it to 3 decimal places and use 0.308. Right? That's fine. So we've got a p hat of 0.308. Remember that our n, in this case, is the number of questions that were written, so 156. We definitely could have talked about, okay, so how many people? 48 picked the paired, I think, right? So we could have talked about that proportion. 48 students out of 78, that's a different proportion than the 0.308, right? But we could have talked about that proportion, but now I'm just talking about, I decided to just level it out and say, okay, well, out of all the questions that were written, 0.308 people, or the proportion of people who chose to write the paired question is 0.308. So we've already talked about our null hypothesis, but we want to compare our proportion to 0.25, right? Is it going to be different from 0.25? We already know that 0.308 is larger than 0.25. We want to know if it's significantly larger than 0.25. And so if we want to know if people prefer the matched pairs questions, then we suspect that P might actually be larger than 0.25, making this a one-sided test. To do the test, I'll zoom in here. We've got our P hat, which is the 0.308. You've got your hypothesized P, which is 0.25. And then down here, we've got your hypothesized P, and then 1 minus that, 0.25, 0.75, and then over N, which is 156. We do this calculation, and we find that Z is, rounding Z to 2 decimal places still, Z is 1.67. Not very big, right? Not quite past 2, but we'll see what we can do here. So find your p-value is the same as we were doing for one sample mean sigma known. We use the Z table, and so using the Z table, we find the area to the left of Z equal to 1.67 is 0.9525. So the area to the right is 0.0. I've got double decimals in here. Double D's. Oops. That just says oops. What we're talking about, if we wanted to draw a normal distribution, Z is centered on 0, and now we've got a Z of 1.67. Our null hypothesis was that P is 0.25, and the alternative was that P is greater than 0.25. Because you want to know if it's greater than, this area is your one-sided p-value. Because I know we've been using the t-table a lot, but just as a refresher. Because the t-table is nice, right? Because it gives you the one-sided and the two-sided p's, so you don't really have to think about it. But now for the z's, we have to say, okay, well, which area do I want to find for my p-value? So we find a one-sided p-value of 0.0475. 0.0475 is less than 0.05, right? I didn't tell you what alpha level to use, so we'll use the default. But it's really on the cusp, right? 0.0475 is really close to 0.05, right? So it's not clearly beyond that. So when you've got situations like this, yeah, it's less than 0.05. But what I've got a little note about here, and it's kind of important, is you have to think about, well, are there consequences to rejecting the null hypothesis, right? Because if you're only rejecting because of this, well, that's not really strong evidence, right? And so, for example, if based off of this p-value, you're gonna shut down a factory or something, you might wanna think twice about that, right? Or if you're based on this p-value, you're gonna have to buy, you know, millions of dollars worth of machinery to upgrade. Well, it's not that strong evidence, right? Yeah, it's less than 0.05, but it's not really, really less than 0.05, right? So you always want to think about, okay, in this case, does it matter if we say, oh yeah, matched pairs is the preferred question, or no, it's not the preferred question, not really, right? And so for us, what we're dealing with, the consequences are minimal, right? But you guys did a question about the type 1 and type 2 errors. Right? Here, the probability of a type 1 error is the p-value, right? This is the probability that we reject the null hypothesis when we shouldn't have. That's pretty large. I think 4.75% is quite large, right? And so even if we took it the other way and said, okay, well, what if we had a two-sided test, right? If we had a two-sided test, then we would say, okay, well, that's my one-sided p-value. I have to replicate it down here, so I can just multiply it by 2. Then all of a sudden, my two-sided p-value is 0.095, which all of a sudden I wouldn't reject the null hypothesis. So this is also the reason why we use the two-sided test, so the not equal to, as our default, because it makes it harder to reject H naught, right? It just makes it a little bit harder to reject the null hypothesis because you have to be a little bit further out into the tails in order to reject it. Any questions? I've got a little blurb in here. It's in the lab too, but I figured I may as well throw it in here. Right, we can definitely use the prop.test function, which takes x, which is the number of successes. It takes n, your sample size, and p naught, which is your hypothesized p. What do you want to compare it to? I added the correct equals false. It's not something you have to worry about, but just to get results that are the closest to ours doing it by hand. So I'll just make a note here. It's really not that important, but to get our results as close to the results we found by hand. We found by hand. It's just saying don't do this continuity correction. Of course, there's lots of different formulas that we could use, more sophisticated ones. But what's nice about using The z-test is that, well, we've seen the z distribution, we've got the z table figured out already, and so it just eliminates a lot of the work. So here, it finds our one-sided p-value of 0.04805, which is not that different from 0.0475. I could have sworn when I first started using the prop.test function, it did a z-test, but now all of a sudden it's changed its gears to do a chi-squared. Well, the x is actually a chi, a Greek letter chi. And it looks like a fancy x. Chi-squared is, it's spelled chi, C-H-I, and then squared, chi-squared. I've got it on the outline as if we're covering it, but I really don't think that we're gonna have time to get there. So, and I'm not too worried about it. It's not on the final, so. It means we can cut it. So, but just the chi-squared is just another method of testing categorical data, and it can handle multiple groups as well. And so in our conclusion, right, since our one-sided p-value of 0.0475 is less than our sigma alpha level of 0.05, we have enough evidence to reject H naught in favor of H8. Therefore, there is evidence that paired data is the preferred question type. I'm kind of stretching the truth a little bit. All I can really say, truly, is that it was the most chosen question type. Maybe not preferred. Is the preferred. Doesn't make sense to say most chosen, but it's the chosen one. Oh, I thought I had a page break in here. Oh well. We can do this with the other data, right? So consider the previous example where only 25 people chose to do a one sample mean question with sigma known out of a total of 156 questions completed. Out of the 4 different choices in the sample evidence that the one sample mean with sigma known is the least popular type of question. More like, is it the least chosen one? But we'll talk about, is it, you know, a preferred question or a least favored question, just for simplicity's sake. Okay. Like I said, I wanted to have a page break in here, but I didn't. You know what? Let's talk about I'm just thinking, no, let's just do this one. It's the same-ish, right? But just to get practice in writing it out ourselves, right? me typing it up and you writing it out is a little bit different. So we've got, okay, so 25 of the 156 questions were the one sample mean sigma known question. Right? And so for this example 2, what we'll call a success is the sigma known question. Typically, we denote the number of successes by X, if you want to. So X is the number of successes. Which in this case is what, 25, I think? Yeah, 25. And N, which is your sample size, is out of the 156. So we can start by finding our p hat. P hat is X over N, right? The number of successes over your total sample size, which is 25 over 156. .16025,641. We can just round it to 3 decimal places, 0.160. Rounding to 3 decimal places. As good as any. Yeah. Unless the p hat is really small, then you'll obviously want to make room for more. You don't want to use a p hat of 0. But if it's nice and big like this, then you can just go to 3. Okay, so just as a little note, we want to know if 0.160 is significantly less than 0.25, right? Back to that 0.25 where we've got these even groups, is less or significantly less than 0.25. So already you know that your H naught is at P equal to 0.25. You've got your sample proportion, 0.16. You want to compare it to 0.25, and so 0.25 is in your hypothesis. Our assumptions that we have to check. First thing we have to check, well, is the random condition. We assume students were randomly selected. Not exactly the case, but it is an assumption that we're making. N less than 10% condition. Here I would say something like, it is reasonable to assume that a sample size of 78 students is less than 10% of the population of students, right? I'm not talking about the number, the questions written here, because in the grand scheme of things, these questions came from the students, and so I've sampled from students. Right? Like I said, a little tricky just because everyone chose 2 questions. It'd be easier if everyone just chose 1 question and then you would all have your 1 question. Well, now you tell us. I know. Would have made my analyses much easier. But, oh. So here you can say something like, it is reasonable to assume uh, 78 is less than 10% of the population of, let's say, statistics students. We'll narrow it down that far just because, yeah, you have to be in stats to write a stats test. But I'm not going to specify at the college or in the world. And then do a little mark here. Another page. Oops. So for hypothesis testing, because that's all we're doing in this question, we have to check that n times p naught, which is 78 times 0.25, which I can't remember, 19.5, is more than 10, and then I throw a little check mark. Just saying, yep, bigger than 10, moving on. And NQ naught is 78, oops, times 0.75. 58.5. You could have just done 78 minus 19.5 is 58.5, right? Because we're just splitting our 78 into 1/4 and then 3/4. But either way. Right. So then we can say, therefore, the assumptions for inference are satisfied. You don't have to say that. If you just go on to do the question, that's fine too. The assumptions for inference are satisfied. I only say it because I had a separate little section there saying, are the assumptions for inference satisfied? And that's what this is supposed to lead you to. Now we can do our hypothesis test. Right, so now our step 1 is still state the hypotheses. My null hypothesis, we already established, is that P is 0.25. And my alternative hypothesis in this case, right now I want to know if 0.16 is less than 0.25. So now I want to know if it's less than 0.25. I've still got a one-sided test. It's just on the other tail, right? Just make a note here. This is a one-sided test because I only care about one side. Oops. Step 2. Do the test. Z is P hat minus P naught over the square root of P naught Q naught over N. So P naught we said was 0.160 minus, or P hat, sorry. And then P naught was the 0.25. over the square root of 0.25, just to emphasize that Q naught is just 1 minus P naught over N, which is 156. .16 minus 0.25 is negative 0.09 divided by the square root 0.25 times 0.75 is 0.1875 divided by 156. It snagged my square root. It's probably way down here. There it is. I'll just show all my steps here just until we get used to doing these calculations. And then what you can do is you can just skip from filling in the values to the end if you want. 0.1875 divided by 156. So I got negative 0.09 divided by the square root of 0.00120193. I'm going to store this. Let's say for a second that you forgot to take the square root. Then you get negative 0.09 divided by 0.0012. You would get a Z of 74.85 or 88, sorry. So just as a little side note, yeah, that is possible, right? It's just very, very unlikely, right? So if you're getting these huge Z scores, then a good check-in point is just, did you forget to do the square root maybe? Because if you forget to do the square root, then yeah, you're gonna end up with these huge Z scores all the time. And I see a forgotten square root is probably the most common mistake. Well, forgotten squares and forgotten square roots. So just as a heads up, if you're getting these huge Z scores, you've probably forgotten to take the square root. So then recall one square rooted is 0.034668762. So 0.09 negative divided by that guy. Oh, what the? Did the wrong number. Square rooted. Guess I better store that. I get negative 2.59. Checking out there. So are you guys getting? Okay, good. Then I'll keep writing. 595996918. So Z has to have only 2 decimal places, right? So if we're rounding this to 2 decimal places, we get negative 2.60. That's far out into the lower tail, right? 2.60. Already we suspect we're going to reject the null hypothesis with more evidence than the first time, right? So step 3, find the p-value. If we just draw it out, Z is centered on 0, and we found a Z of negative 2.60. We want to know if it's significantly less than this, so that means this is the area that we're looking for. So this is your one-sided p-value. A Z of negative 2.60. So we're going to use the Z table. So using the Z table, oops. You always find the area to the left first, but that is the area that we want, so that's good. So we find the area to the left. The area to the left of z equal to negative 2.60 is, okay, here we go, negative 2.60 is 0.0047. So our one-sided p-value is 0.0047. That's a lot smaller than 0.05, right? So we can reject the null hypothesis. So step 4, sorry, is the conclusion. Since our one-sided p-value, if you had to find your two-sided p-value, right, you would just multiply your one-sided p-value by 2. So since our one-sided p-value of 0.0047 is less than our assumed alpha level of 0.05, we have enough evidence to reject H naught in favor of HA. May as well throw that in there. Therefore, as a conclusion, just because I'm running out of space here, right, we're talking about the one sample mean sigma known question type, right? Sigma known questions are the least favorite, more like the least chosen, but the least, is that the right word? Anyways, therefore, sigma known questions are blah. No. Are the least chosen question type. Can't remember what the exact question was. All right. Any questions about that one? Yeah. So, yeah, that's a good point, actually. I only use the p-value approach, but what you could do is there's another way that you could do it, and you could use a critical value. And so if you're using an alpha level of 0.05, so if you go to your t-table, if you're using an alpha level of 0.05 and you've got a one-sided test, what it's telling you is that any z-score larger than 1.645, you're going to reject the null hypothesis. Right? So you could go the other way, and that goes for t's too. But just to keep things as simple as I possibly can with this stuff, because there's a lot going on, I don't do that, but if you want to do that, you can. All right. We'll end it here. Do confidence intervals next day. But like I said, you can definitely start plugging away at assignment 6, and then it's due on Wednesday next week. See you later. Oh yeah, grab yeah, it's just this one wasn't on there, so everything else is whatever. Just kind of maybe do some old school cut, copy paste.